recorded. So yeah, you can continue, Zach.
So my teacher said if if a body A exerts a force on body B, then body B will simultaneously exert a force on the body. The forces are equal in magnitude but opposite in direction.
Exactly, like that's the perfect explanation for Newton's third law. So when it comes to Newton's third law, let me just try to use this. This is gonna be a box, and we're gonna label this box A. So different color, different color. Um, and then let's draw another one right next to A. Uh, which color can I use? Blue. Um, I'm pretty sure it does look like a different shade of blue, right? Because I don't want it to be exactly the same color. So basically, what Newton's third law states is that if this body pushes or applies a force on this other body, body B will also apply a force on body A, and both these forces are equal in magnitude, but in different directions. I'm pretty sure you can already see that this is going to the right, and the force that B is applying on A is going to the left. So basically, what this means is that if body A is applying a force of 20 newtons on body B, so you remember that force is a vector, so it has a direction and a magnitude. So it's applying 20 newtons to the right, and body B will apply a force of negative 20 newtons because it's going to be in the opposite direction. But as you guys remember, I said when it comes to stating the direction, it just depends on what you prefer to use. You can use to the right, you can use to the left, you can use signs, you can use north, west, east, as long as it gives you a sense of direction. So basically, what happens most of the time with Newton's third law is that most people don't understand that Newton's third law is something that actually happens in a very small space of time. If you look at it, like it can occur in a very small short space of time. Like it's sorry, instantaneous. It's instantaneous. So it's like right now, let me ask you this, guys, this question. When you're driving a car and you ram a fly, is the force that you are applying that is the force that your that your that your car applies on the fly equal to the force that the fly applies on your car? Sorry about that thing. Um, can you answer that?
So can sir repeat the question, sir?
Okay, sorry. Um, so let's say you're in a car and you're driving and you ram into a fly. You know how small a fly is. So in that instant, is the force that your car is applying to the fly equal to the force that the fly is applying on your car? according to Newton's laws.
Yes, sir. According, sir.
Exactly. So it doesn't matter how big or how small the objects are, the forces will always be equal and they will always be in different directions. So that's why I'm saying Newton's third law and Newton's first law is sort of like a concept because it just gives you information that okay, when you're gonna get a scenario in which this object is pushing against this other object, you should know that there are equal forces acting in between those two objects, and those forces are in different directions. So usually, if they want a mathematical representation of Newton's third law, you can just say force of A on B is equal to force of, oh yeah, sorry. Yeah, it's equal to force of B on A. But since you know it's gonna be in the opposite direction, you can put negative on this side or put negative on this side. And yeah. So you can just say negative force of A on B is equal to force of B on A. This negative is for is to indicate that it's the directions are opposing. So that's basically what I can tell you about Newton's first and second law. And now we're gonna go to Newton's first and third law. And now we're gonna go to Newton's second law, which is the more complex one. So can you guys mm, can one of you tell me Newton's second law? Let me just stop this. Jason, can you tell me Newton's second law? Okay,
Yes,
Kyle.
sir. Force is equal to the rate of change of momentum times gravity.
And like,
So I can answer.
yeah, you can answer.
It says that when a net force acts on an object and it causes the object to accelerate in the direction of that force, and that acceleration is directly proportional to the net force and inversely proportional to the mass.
Thank you. Thank you. That actually makes me feel a bit more safe. Sorry. So, Jason, Kyle's definition was correct. Jason, like as I've said, you are saying like some high level shit. Sorry for cursing. You are saying like higher level. You're giving me a higher level into definition. Like you guys haven't learned about momentum, so you can't be giving your definitions in terms of momentum because you don't know what momentum is, or like academically they don't expect you to know what momentum is. Like obviously, like if you go outside you'll know what momentum is, but academically at your level they don't expect you to know what is momentum. But honestly, like what did you say your definition was again, Jason? So,
Force is equal to the rate of change of momentum times gravity.
rate of change of momentum
Times gravity.
uh, rate of change of momentum, that's going to be delta P divided by delta T and multiplied by gravity. Okay, let's prove this. Right, so momentum, that's velocity multiplied by mass, and this is in seconds, and velocity multiplied by mass, that's going to give you kilogram meter per second. And when you're gonna, since this time is below, it's gonna also multiply by meter per second also. If I remember well, we know that F net is equal to MA, and we know A is in meter per second square. And M is in kilograms. So we know that 1 Newton is equal to kilogram meter per second square. So that's the value of 1 Newton. That means we have to get a Newton on this side. But since we're multiplying by gravity, Jason, what sort of gravity? Like, are we talking about like gravitational acceleration or gravity as in weight?
Gravity is constant, so 9.8 meters a second square.
Okay. So basically what you're gonna end up with, if this is the constant, you're gonna end up with meter per second square on the gravity as well. So what you're gonna see happening is that this is kilogram meter per second square. This is a Newton. But now you're gonna multiply with meter per second square again. So you're gonna end up with kilogram meter square per second to the exponent 4. So as you can see, this does not give you 1 Newton. So yeah, I think this just proves that your definition is sort of correct. Actually, you know what? It's wrong, but force is equal to the rate of change in momentum. That's what you're gonna learn in grade 12. You will learn that force is equal to the rate of change in momentum. I think they call it inertia or something like that. I think it's inertia. So this is what you will learn in grade 12. So this gravity does not exist when it comes to force. So yes, you can say that force is equal to the rate of change in momentum, but that's the definition for inertia. That's not the definition for Newton's second law. When it comes to Newton's second law, it's F net is equal to ma. That's the equation that you should get after defining Newton's second law. The equation that we got after applying Jason's definition is for inertia. So Jason, like Newton's second law states that when an object is acted upon by an unbalanced force, the object is gonna accelerate, and that acceleration is directly proportional to the force that was applied and inversely proportional to the mass of that object. I just hope that's that's that suits you. That takes you well. You understand that now. So guys, Kyle and Zach, do you guys understand what we mean by things are directly proportional and indirectly proportional? But okay, most of the time I'm gonna say inversely proportional. Just know when I say inversely proportional, it means indirectly proportional. So do you guys understand what we're talking about when we talk about proportionality?
Yes, sir.
Okay, okay. Can you explain it to me?
Sorry, sir.
Can you explain it to me?
Newton second law, sir.
No, 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 no. I'm just asking, do you know what we mean when we say two things are directly proportional or indirectly proportional?
So, right, sir. So I don't think I understand, sir.
Okay, so we're gonna take Newton's law, second law, for example, right? So,
Oh, wait, sir. I think I do, sir. Even when I'm
okay,
reading this example, sir.
okay. Can
So
you
must
type
I
it?
read the example, sir?
Yeah, it's fine.
So this example that the sir gave us, sir, he said, as a car accelerates, your body accelerates with it, and you feel the back of the chair pushing you forward.
Yes,
When
yes,
when the car and you reach constant velocity, you no longer feel the chair pushing from back.
yeah.
What happens when the car? And then he asks, what happens when the car suddenly stops?
So you have been in a car, no?
Yes,
And
sir.
then when like you just apply the brakes out of the blue, like you move forward a bit, no?
Yes, sir.
That's because like your body needs time to, let's say, if the car is moving at 20 kilometers, you're also moving at 20 kilometers, right?
Yes, sir.
And then when the car suddenly stops, the car is no longer moving, but your body is still moving at that 20 kilometers.
Yes, sir.
So that's why you need a seat belt. You need a seat belt because the seat belt is there to stop you from like jumping out the car when the car suddenly stops.
Yes, sir.
You still have like some momentum, but that's something that you'll tackle later on. So let me just explain like direct and inverse proportionality like very quick.
Yes, sir.
Okay. So when we state Newton's second law, we say an object is and if an unbalanced force is applied on an object, the object will accelerate. So we're gonna focus on acceleration in accordance to the definition. And the acceleration of that object is directly proportional to the force. And we're gonna use this sign to indicate direct proportion. So force, we're gonna have our net force here. If I remember well, this is the sign for direct proportion. Let me just search it for it real quick. Um, direct proportion. Directly proportional. Yeah. This is the symbol for direct proportion. And that acceleration is also indirectly proportional to the mass of the object. So when we say something is indirectly proportional, you have to write it like this, or you can write it the other way around. Like the problem is that the sign gets harder to draw when it's indirectly proportional. So these indicate that these two things are indirectly proportional, and this one uh, indicates that these two things are directly proportional. Or if you want, you can also use this, but also if you want to show direct proportion using this one, you're just gonna say something like this. Let me just see if I can draw it. I don't know. 1 over f net. So it just depends on which symbol or in which direction you're able to draw this symbol. And then you can choose your direct and indirect proportion in accordance to the direction. So this is basically how Newton's second law came about. If you look at it like this means that A, let me just erase this. This means that A is equal to F net this F net and multiplies by 1 over m. And then this is gonna go up here, and then you're gonna end up with A is equal to F net over m. Now, sorry, undo that. Now, if you look at all of this is the exact same thing as this equation. And I'm pretty sure you guys are aware, are familiar with this equation, F net is equal to MA. So this is just how this equation is derived. It's just that, you're gonna cross multiply. This is gonna be A over 1. You're gonna cross multiply. This is gonna go here, and this is gonna go there. And then you're gonna end up with F net is equal to MA. So basically, Newton's second law, the definition, is gonna give you this equation. It's gonna give you the equation in terms of acceleration. But when you're gonna write it down, we're gonna make force the subject of the formula, and we're gonna write it as F net is equal to MA. So for the direct and inverse proportion, if you look at it, let's say F is equal to 2, our F net is equal to 2 newtons, but our mass is equal to 4 kilos. We're gonna end up with 0.5 as our acceleration, 0.5 meters per second squared as our acceleration. Can you just end this quick and then come back, because it's gonna cut at any point now. So please, I'm just gonna end the meeting and then we'll come back now.
Yes, sir.
Yes, sir.
Cool.